Okay, we are still in section 2.6, limits at infinity. And now we want to talk about example 19, limits at infinity of rational functions. So hopefully you recall that a rational function is a polynomial divided by a polynomial. So we have in this case an example of a polynomial, a quadratic divided by another quadratic. And we want to take the limit as x approaches infinity. So either plus or minus infinity. In this first example, x approaches infinity. The way you handle limits of rational functions as x approaches infinity or minus infinity is you look for the highest power of x in either the numerator or the denominator. Notice that the numerator has x squared, the denominator has x squared, so the highest power of x I see anywhere is x squared. So what I'm going to do is multiply both above and below by 1 over that highest power of x. So the numerator will be multiplied by 1 over x squared, the denominator will be multiplied by 1 over x squared. So then as I multiply that through by each term, I get 5x squared divided by x squared becomes 5. 8x divided by x squared becomes 8 over x. Minus 3 divided by x squared becomes minus 3 over x squared. Then I have 3x squared divided by x squared becomes 3. And then I have 2 divided by x squared, so I get 2 over x squared. Now I can take the limit of this piece by piece. The limit of a constant stays constant, so the limit of 5 is 5. The limit as x approaches infinity of 8 over x, so 8 over a big number, 8 over a large number, getting larger and larger, gets closer and closer to 0. 3 over a large number gets closer and closer to 0. Limit of a constant stays constant, so the limit as x approaches infinity of 3 stays 3. 2 over a large number gets closer and closer to 0. So you add all these up, I get 5 plus 0 minus 0 is 5. 3 plus 0 is 3, so the answer is 5/3. And if you were to look at a graph of this function, this graph is not to scale, but what you can see is that as x gets closer and closer to infinity, as x gets really big, this graph is approaching an asymptote at y equals 5/3. So this function is getting closer and closer to 5/3 as x approaches infinity. In part B of this example, we are looking at 11x plus 2 divided by 2x cubed minus 1, this time as x goes to minus infinity. It's handled the same whether it's plus or minus infinity. So the first step is to look for the highest power of x that you see, and I see that the highest power of x is x cubed, which occurs in the denominator. So I'm going to multiply both the numerator and the denominator by 1 over that highest power of x, 1 over x cubed. So 11x over x cubed is 11 divided by x squared. 2 over x cubed, 2 over x cubed. 2x cubed divided by x cubed is 2. And minus 1 over x cubed, so minus 1 over x cubed. Then I take the limit of this piece by piece. As x gets big, whether it gets big positive or negative, doesn't matter. I still have 11 over a huge number, gets closer and closer to 0. 2 over a huge number gets closer and closer to 0. The limit as x approaches infinity of 2, a constant, stays constant, so that's 2. And then 1 over a huge number gets closer and closer to 0. So I get 0 over 2, which is just 0. And if I were to look at a graph of this guy, as x approaches minus infinity, this function is getting closer and closer to 0.